In this video, I'm going to continue from the last one. We are discussing about MPEG, MPEG compression technique. I'm starting from this point where I'm concluded the last video. The reference between the different types of frames realized by a process called motion estimation or motion compensation. The correlation between two frames in terms of motion is represented by a motion factor. So the correlation between two frames in terms of motion is represented by a motion factor. The resulting frame correlation, therefore, the pixel arithmetic difference strongly depends on how good the motion estimation algorithm is implemented. So because here in case of motion estimation, or we actually created three types of frames. One is intro frame, b frame is for the difference, p is the predicted frames, b is the bidirectional frames, and in both of for predicted frames we try to predict from inter frames, and for bidirectional frame we try to create that forward or backward frames, and all these three are related, and that is why we need to correlate those frames, because we are going to reduce some data from those intermediate frames. So we need to correlate those data among the frames so that the things can be compressed and decompressed as per requirement. So that is why the resulting frame correlation, and therefore the pixel arithmetic difference strongly depends on how good the motion estimation algorithm is implemented. So good estimation results in higher compression ratios and better quality of video or coded video sequence. However, motion estimation is a computational intensive operation. So try to understand this. Motion estimation is a computational intensive operation which is often not well suited for real-time application. Figure 4 shows the steps involved in motion estimations, which will be explained as follows. So here you can see this is the figure 4 schematic process of motion estimation adapted from admin reference 8. So here actually what is that? Frame segmentation. The actual frame is divided into non-overlapping blocks. Non-overlapping blocks usually 8 into 8 or 16 by 16 pixels. The smaller the block size are chosen, the more factors needed to be calculated. So it depends upon your computation load your machine can take, or the process you can go far. In that depends, depending upon that you can divide the block, but smaller the block size or block size, more factors will need to be calculated, because more number of vectors will be created. The block size therefore is a critical factor in terms of time performance, but also in terms of quality. If the blocks are too large, the motion matching is most likely less correlated. So here it is said that block size therefore is a critical factor in terms of time performance, but also in terms of quality. If the blocks are too large, the motion matching is most likely less correlated. If the blocks are too small, it is probably that algorithm will try to match noise. MPEG usually block sizes of 16 by 16 pixels. Next one is search threshold. In order to minimize the number of expensive motion estimation calculation, they are only calculated if the difference between two blocks at the same position is higher than a threshold. Otherwise the whole block is transmitted. So in order to minimize the number of expensive motion estimation calculation, means rather than going for motion estimation for every frame, we are trying to minimize the number of expensive motion estimation calculation by doing what? By doing like they are only calculated. Motion estimation will be calculated if the difference between any two blocks at the same position is higher than a threshold. Then only we will go for motion estimation calculation. Otherwise the whole block is transmitted without calculating the motion estimation. Block matching, this is the third point. Here you can see in this one also frame n or frame n-1 is frame initial frame, the next frame or previous frame is a frame segmentation blocks, then search the threshold, Okay, blocks threshold, if it is matching then block matching, and then go for next step, that is block matching. So in general block matching tries to stitch together. So in this process block matching tries to stitch together an actual predicted frame by using snippets from previous frames. The process of block matching is the most time consuming one during encoding. So this is the part where motion estimation process takes most amount of time. This process of block matching is the most time consuming one during encoding. In order to find a matching block, each block of the current frame is compared with past frame with a search area. So they try to find out uh, similar pattern or area within a range of frames. So that is the point, block matching. Point is that in order to find a matching block, each block of the current frame is compared with a past frame within a search area. Only the luminescence information is used to compare the blocks. So only luminescence information is used to compare the blocks, but obviously the color information will be included in the encoding. Though the luminescence information is used to compare the blocks, but the color information also included in the encoding. The search area is a critical factor. Try to understand this point. The search area is a critical factor for the quality of the matching. That's because we might go for larger search area, we might go for smaller search area, and that is why this is a critical factor for the quality of matching. If it searches a larger area, so it is more likely that algorithm finds a match block if it searches a larger area, but obviously number of search operation increase quadratically. That is the point. If you choose for a larger area, then your computation will increase quadratically, means in a power of 2. That is the point. And if you choose smaller area, then obviously there will be less chance to get the similar pattern or similar matching block in that area. So that is the point. The search area is a critical factor for the quality of the matching. Obviously number of search area in search operation increases quadratically when extending the search area. Therefore two large search areas slow down the encoding process dramatically. To reduce these problems, often rectangular search area are used, which take into account that horizontal movements are more likely than vertical ones. So more detail about the block matching algorithm you can find in the reference 9 and 10. Next one is prediction error coding. So video motions are often more complex, and a simple shifting in 2D is not a perfectly suitable description of the motion in the actual scene, causing so-called prediction error. The MPEG stream contains a matrix for compensating this error. After prediction, the predicted and the original frame are compared and their differences are coded. So try to understand is that while you try to predict the new frame, then obviously there will be some errors. So what it does to minimize that error, to compensate that error, that MPEG stream contains a matrix of compensating this error or compensation values. So what it does, how it contains those values. After prediction, the predicted and original frames are compared, and whatever the errors are or whatever the differences are, those are stored in those matrices, which that matrices contain the compensating error, and that matrix will be inputted in the MPEG stream. Obviously less data is needed to store only the differences. So here in this scenario you can see this is the iframe, this is the motion vector, means that is the arrow motion vector. Forward predicted frame means it might be go there, and again forward predicted, this is the forward predicted frame plus prediction error some and the resulting frame is this one. So prediction error is somewhat this much, somewhere around this one. So resulting frame is this one. So in that way, having the prediction error, it might get the resulting frame. So here you can see a iframe, intra frame is this one, but our actual frame need to be this one, but after prediction it get this one. So having the prediction error, we can get this one. Okay, so only so rather than having all the images, all the frames, all the high image resolution frame, we can have only this one, and we can directly predict this one, and having the information of prediction error, we can create actual frame. Next one is vector coding. After determining the motion vectors and uh, evaluating the correlation, this can be compressed. Large parts of the MPEG videos consist of B and P frames as seen before, and most of them have mainly stored motion vectors. So try to understand that in B and P frames only the motion vectors are stored. These motion vectors are stored. Therefore, an efficient compression of motion vector data, which is usually high correlation, is desired. So, an efficient compression of motion vector data which has usually high correlation. These motion vectors have usually high correlation. So, we need the efficient compression on those motion vector data. So, then we'll go for a compression of this data using different compression technique. After that, it will go for block coding. See discrete cosine transform below. So in that step, we'll go for discrete cosine transform, which has been also discussed in case of JPEG. It is almost same like JPEG, DCT or discrete cosine transform. DCT allows similar to first Fourier transform, or same thing like we have used in JPEG. Please kindly go through that video, or actually no need to go more about this, but try to understand the basic terminology used here. Like it uses same frame blocks like 8 into 8 or 16 by 16 as per requirement, can be represented as frequency components, because we are transforming everything in frequency domain. The transformation into the frequency domain is by the formula, so it uses this formula. And the inverse of DCT is this one. And again, DCT is unfortunately computationally very expensive, and its complexity increases disproportionately. That is O(n) squared. This is the reason why images compressed using DCT are divided into blocks. That is why we are dividing into blocks. So here you can see figure visualization of 64 basis function of a DCT reproduced from 12. So in that way, it go for this step. And the fourth step, that is quantization, which is same like frame wise quantization is happening here, same like JPG quantization. During quantization, which is the primary source of data loss, because we are going to round up the this fractional value also. That is why we are going to lose the data. The DCT terms are divided by quantization matrix, which takes into account human visual perception. The human eyes are not reactive to low frequencies than to high ones. So higher frequencies end up with zero entry after the quantization, and the domains was reduced significantly. Where in this equation you can see where Q is the quantization matrix. Q is the quantization matrix of dimension n. The way Q is chosen defines the final compression level, and therefore the quality. So in that way it will go through like this. So the AC terms are then here after the quantization. DC and AC term are treated separately, as the correlation between the adjacent blocks is high. Only the differences between DC terms are stored. DC terms are stored, and instead of storing all values independently, the AC terms are then stopped, stored in a zigzag path with increasing frequency values. The representation is optimal for the next coding step, because same values are stored next to each other. As mentioned, most of the higher frequencies are zero after division with Q. So as like JPEG, it is also takes same type of structure, zigzag path for storing the frequencies, higher to lower or lower to higher. So in that way we try to quantize the whole frame in a frequency domain. After that it will go for entropy coding. The entropy coding takes two steps: run length encoding and half band encoding. These are well known lossless compression methods which can compress data depending on its redundancy by and additional factor 3 to 4. So here we can see that run length encoding and Huffman encoding is used, which both of them are lossless, not lossy. We only lose data in case of quantization only. Maximum information losing happens in the quantization only. So here you can see all 5 steps together, frame 1, frame n-1 and frame n, 2 frames, and then it is difference image. So then it go for motion factors, motion estimation. Then for each mesh block, macro block of 16 by 16 pixels, it will get the motion factors. Also that in parallel it will go for DCT, quantization, and RLE, run length encoding. Then ultimately combining all those things, it will go through Huffman coding. It will get the compressed MPEG video. So this is the main picture. First n-1 and frame n, and getting the difference between these two image, difference simple negative. Okay, then we'll get the difference image, and that difference image will go through motion factors or motion estimation, and also it will go through parallelly with DCT, discrete cosine transform. It will go through quantization, then run length encoding, then all of this will go through Huffman coding. Then it will go create the ultimate product, that is MP4 or MPEG version. So illustration of the discussed 5 steps for a standard MPG encoding. As seen, MPG video compression consists of multiple conversion and compression algorithms. At every step, other critical compression issues occur, and always from a trade-off between quality, data, volume, and computational complexity happens. However, the area of use of the video will finally decide which compression standard will be used. Means area of use of the video means what is the field where you are going to use the video is the main point to decide what type of compression method you are going to use. Most of the other compression standards use similar methods to achieve an optimal compression with best possible quality. So try to go through this context again. Many more things to learn about MPEG layers, and actually there are various versions. Some might be updated, some might be not updated. That is why you might find differences between them also. And also try to go through these references. Some of them has been cited very importantly, very definitely, and some explanations are not here in this context or in this text or in this content. So you might find other information also in the reference sections. Please go through this. This is very interesting and need to be learned topic. And if you have any problem with this, please let me know. I'll try to resolve that thing over Google Meet. Thank you.